did.
To call the meeting of Energy and Climate together and ask for approval of the minutes. Representative Christensen.
Thank you, Madam Chair. I move to accept the minutes from January 17th. Excuse me, is it January 17th? Yeah, January 17th, please.
Is it 17th or 22nd? It's the 22nd.
Actually, I think it was the 22nd.
Okay, I stand corrected, I think. Yeah, it's January 22nd. I move to accept the minutes.
Thanks. All those in favor say aye.
Aye.
Any opposition? Okay, the minutes are adopted. Before we get started and welcome our guests, I just want to tell you, this is the fourth of our hearings that's basically science and data. And now we're going to move into a somewhat different set of hearings talking about some solutions. We'll start next week with energy efficiency, and that's scheduled for Tuesday, and we're lining up something I think that's going to be a lot of fun for you on Thursday about successes. There will be opportunities both Tuesday and Thursday for public comment, and so we'll make sure we'll save enough time for that. And with that, for this morning, I'm going to introduce Dr. Ned Mohan from the University of Minnesota. We're going to take a deep dive into the electric grid. And so as we go forward and maybe think about some changes, we have to have this basic understanding. So with that, welcome to the committee, and if you'd put your name on the record.
Thank you. Good morning, everybody. Good morning, Madam Chair and committee members and all those who are here. You see the snapshot of our university, your university really. How many universities can brag that the mighty Mississippi flows right through the campus? So today's topic is electric power systems, how they work, present status in Minnesota, and future with renewables. So my name is Ned Mohan. I have been with the university for the last 43 years, and I see a few young people here. I think this was before they were born, I think. And so I am joined here by Mark Ahlstrom to my left, who is VP of Renewable Energy Policy and also with NextEra Energy Resources. And so Mark has been very kind and generous, and anytime we needed some help, Mark dropped everything and supported us. And same thing with Jukka Kukkonen here. Anything you want to know about electric vehicles, you can ask him. I leased a Nissan Leaf recently based on his advice. I paid a little too much for that lease, but I'm not blaming you. I didn't negotiate. I gave whatever they asked. Coming from India, that's a very unconscionable thing to do, but I did. Okay, so outline for today is electricity and how we can integrate renewables into it. And then Mark will talk about renewables as modern power plants. And then Jukka will tell us about prospects for EV. Okay. So I got this slide from Dr. Phil Peterson at our university, and I always use that now to show how little we know, humility. So here, Lewis Thomas talking about the greatest accomplishment of 20th century, science has been the discovery of human ignorance. So what's new about that? We have known that for a long time. Okay. And then this philosopher, emperor of Rome, saying everything we hear is an opinion, not a fact. Everything we see is a perspective, not the truth. So anyway, electricity is a basic human right. I learned that a long time ago, and the unfortunate fact is that 1.3 billion people, 1/6 of humanity, have no access to it. And in a very short time, we'll be joined by 1 billion more people in just a short 10 years. So it took 200,000 years to reach 1 billion. Then it took only 200 years to reach 7 billion. and it'll take just 10 short years to reach 1 more billion. So that's how rapid things are changing in terms of population. And so, my colleagues here were here on Thursday. I was also here, and I heard them talk about the impact of climate change in Minnesota. I'd like to take a little bit of a global view in next 2 slides. So at the university, we had organized a workshop in 2017 where Dr. Gavin Schmidt, he's the director of this Goddard Institute for Space Studies. It's a NASA institute. It's run by Columbia University. So how many of you have seen the show Seinfeld? Could you raise your hand? Seinfeld, right? Okay. So they go to a restaurant. That restaurant is in the ground floor of this building where Dr. Gavin Schmidt is located. But just a trivia. But the point is that he has a whole slew of people working on attribution and prediction. So they make models, okay? What will happen to this planet as time goes by? So this is the slide he showed us at this workshop where he shows that since pre-industrial age, the temperatures have risen by approximately 1 degree centigrade or 2 degrees Fahrenheit. So does that matter? Well, he says, yes, it does matter. That's close to 1/4 of ice age in the reverse direction. It only took 8 or 9 degrees Fahrenheit to cause ice age. Where, from New York to North Pole were covered in ice, from Spain to Scandinavia. And the water levels had dropped in sea by 400 feet. Okay, so we have already reached 1/4 of ice age. So make no mistake, the poorest of the poor are at the front line. So here is a link here that you see to see half-an-hour video of what Professor Dr. Gavin Schmidt presents. Make sure that you have some antidepressant handy, like Valium or something like that, when you watch that video. So that's your homework assignment. So you thought that you had graduated from school and no more homework, but now you have homework. Okay, only kidding. So moving on to the 21st century, he says that if we have business as usual, we make no changes, then you see on the lower right that our planet would have the same temperature as Venus, 800 or 900 degrees Fahrenheit. Life would be impossible. And then he rules out aggressive mitigation, where we should have started some time ago to reduce the emissions 0 by 2050 and negative after that. So he thinks that in this political climate, that is almost impossible. So he rules that out. So what remains is serious mitigation. And even under serious mitigation, there will be places where temperatures would rise to 400 degrees centigrade or 8 degrees Fahrenheit, full ice age unit. So that's a pretty scary scenario that he paints. But he ends at a hopeful note that if governments and societies, individuals, engineers, and everybody else organize, we can possibly beat this thing here. So what's the culprit? Culprit is really fossil fuels. As you can see here, we're injecting as much as 42 gigatons of CO2 equivalent every year. And it's cumulative. CO2 is a very long-lasting gas, so we are accumulating. And in the middle, you see this chart as which are the countries emitting the most. So, if you look at carefully, you see that China is twice the size of United States today. And United States is twice the size of India. But, we have been in the United States emitting these greenhouse gases for a long time. India and China are, newcomers in some respect here. So our transportation has really taken over the carbon footprint from electric power sector. So as you can see, transportation is in blue and electric power is in black. And that is primarily because a lot of our electric generation has shifted from coal to natural gas. Okay, but we want to get rid of both if we can at some point. Okay, so if you look at, this is annual world energy consumption. Okay, so in 2009, you see, I won't See, these circles probably give the impression in 2050, it'll be like 28 terawatt years per year. That'll be our energy consumption. And then if you go to look at reserves, we have fossil fuel reserves of coal, okay, quite a bit. Then we have uranium, we have natural gas and oil, and then come the renewables. Okay, so we have hydro, not much, which can be exploited. Then we have wind, but here comes the sun, okay? So you can see that we have tremendous resources when it comes to solar energy, and sun shines in poor countries as well, okay? So it's pretty uniform. So what's the answer? Well, it's somewhat, what's the word, obnoxious, or whatever it is, but to say that I have the answer, but it's collectively we have to come up with the answer. But my answer would be that we shift all our energy use to electricity, okay? All our energy use, whether it's in transportation or in cooking or heating, we shift it to electricity as much as possible, generate that electricity using renewables as much as possible, and then conserve and have a sustainability mindset. So how many of you have heard of Chris Farrell? He talks about, I think, frugality and things like that on NPR. Have you heard of Chris Farrell? Right? So he came and gave a talk in one of our classes, and he talking about frugality. I always remember that I have this $2 pen, but I treat it as a Mont Blanc. I guard it with my life, okay? So I have not lost it in 1 year. Okay, so that's a kind of sustainability mindset. Not try to buy things, throw it away, and get rid of it. So, but the point is that science alone cannot stop global warming. Human attitudes must change. Okay, so that's really something we should keep in mind. So coming to the topic at hand, renewables and electricity, how clean are these renewables? Okay, so here there's a comparison between coal, wind, and solar, and you see that for coal it's 1,000 grams of CO2 equivalent. When we say equivalent, we include other greenhouse gases like methane and others. Okay, so 1,000 for coal, whereas for wind it's 10, and for solar PVs is 40. So this is coming from NREL, which is National Renewable Energy Lab. So they do this life cycle analysis from cradle to grave, okay? What would it be? So you can see here that wind is 100 times cleaner, and solar photovoltaics are 25 times cleaner than coal. And we know that gas is, has a carbon footprint of approximately 1/2 that of coal. So natural gas is, twice as clean compared to coal. Okay, but certainly wind and solar here. So, but how expensive are they? So this is a very coming from a very reputable source, Lazard estimates, and it shows the range of different sources for generating electricity. So without looking at the details of this chart, all I have done is circled the least that we can expect to pay for these sources. And those are listed in this orange box over here. And you see that for coal, it's $65 per megawatt hour, for gas, $52, for solar, $43, and wind, $32. So you see that these renewables like wind and solar have already reached what we call grid parity. So they are competing with coal and gas, but we have to keep in mind that these are variable resources, right? Sun doesn't shine all the time, we know that, and the wind doesn't blow all the time. So, but they have reached this cost levels, and of course, we don't need to stop here. We have to make them even cheaper if we can to make their penetration deeper. Unfortunately, rooftop solar is still pretty expensive. And I have my own sob story, which I won't tell here. I'm trying to get a rooftop solar as we speak, and it's many hurdles to overcome. So that's something we should smoothen out and reduce the cost of rooftop solar here. So very basic ideas and terminologies and apparatus that we use in electric power systems. So, so here is a diagram, very simple diagram of generation to the consumer. So generation on the left in red, and this could be a fossil plant and generating a voltage at 22.5 kV, okay? And that voltage has to be stepped up by this generating step-up transformer that you see, because it's economical to transmit this power over long distances only at high voltages, because otherwise you will have too many power losses, okay? So can you hear me okay, Alex? Am I speaking loud enough? Yeah, okay. I can be a little closer to the microphone here. So it depends upon the distance. If a distance is large, you will go to higher voltages like 765. If distance is not that large, then you will stay with the lower level, which is 500 kV, which is still a very high voltage, okay? And then you have step-down transformer when this power reaches its end point, and then you have different types of consumers, which are shown in black. And finally, after several transformations, this power gets to us consumers at 120 volts or 240 volts. Okay, so this is a very simple diagram, but in reality, our power system that we have is very complex. In fact, according to National Academy of Engineering, it's the greatest achievement of 20th century that we have such a interconnected grid, which, Canada and United States, they're connected by over 200,000 miles of transmission lines. And there are over 10,000 generators, and the main point is that they're all rotating in synchronism. They have inertia, and they rotate in synchronism. So that's something we have to keep in mind, and then there's even larger network of distribution lines to take this power and then distribute to us consumers here. So just a few pictures of different coal and gas power plants that you see here. Half of our energy in the state of Minnesota comes from coal and gas power plants today. Okay. And then we have hydro. These are massive structures, and they are built for reasons other than providing electricity, because they are used for many other reasons like flood control and things like that. So then we have nuclear plants. Our state is probably one of the few that has two nuclear plants. One is a boiling water reactor and near Red Wing, and then other one is a pressurized water reactor near Monticello. So we have two nuclear plants. So our state is pretty highly nuclear. I think something like 23% of our electricity is supplied by nuclear power. That's why our carbon footprint is much lower in Minnesota compared to other states here. Then inside a steam power plant here, these are massive power plants. But if I could go back to the previous slide here, when I talk about these generating stations, it could be fossil fueled, but it could be a wind power plant, or it could be a solar power plant, right? And when it comes to consumer, we could have a rooftop solar. So we have all those options, okay, as we go forward here. Okay, so nuclear power plants, steam, and so just to give you a brief idea of what goes on in a, for example, coal power plant which generates steam. So you have heat coming into the boiler, which produces steam at high pressure, and that goes through this turbine, or a turbine, whatever you want to call it, and then that turbine rotates the generator. Then we have a condenser to take away the heat, and then we have a pump to, again, pump that water into this boiler. So it's a closed-loop system, and it's called Rankine cycle, but the takeaway of this slide is that typical efficiencies of these thermodynamic cycles that we have in coal plant, for example, steam-based, is 35 to 40%. Okay, so that's somewhat typical of what we can expect in terms of efficiency here. Then we have these combined cycle gas turbines, where air comes in, is compressed, and then we have a combustion chamber where fuel is pumped in, and it's combusted and goes through the turbine and rotates the generator I talked to you about early on. And then there's another stage here, which is steam-based Rankine cycle, which we saw earlier, right? So together, combined, the typical efficiencies of these combined cycle gas turbines would be typically 55 to 60%. So that's much higher than what we saw earlier for coal plants. So that's why the footprint of electricity produced by natural gas is 1/2 that of coal. Okay, so that's one of the reasons. Okay. So then we have power generation, where we have very large generators, which these turbines turn and produce electricity. So I'd like to say more about this in a minute. And then we have power transformers. We have all seen that driving, Highway 280 and Larpenteur, we see a big power station where we have, power is coming in at high voltages, and is stepped up at that point to distribute, right? Just like it's stepped up, it's also stepped down. And then we have high voltage transmission lines. To me, they look beautiful. I don't know what you think, but a little biased, but they look beautiful. Yeah. So these are three-phase system, three-phase AC. So little deeper drive. That three-phase is generated by a generator with 3 sets of independent windings, which are physically spaced 120 degrees around the stator. And so they produce three-phase voltages. So those are shown here. I don't know if you have access to the internet here, but if I click here, maybe it will show up. My mentor, Professor Riaz, he passed away a few years back. He hired me, but he made these beautiful animations here. So you can see here that this rotor is turning, and it's producing this magnetic field north and south, and it's cutting these three-phase windings, one shown in red, one shown in green, one shown in blue, and you can see how, as a function of time, they are producing three-phase, these sine wave voltages that we see here. So, like they say, picture is worth 1,000 words, right? So then we have this high voltage power transmission. We have all seen these towers, right? And so these towers have these conductors which carry the electricity, electrons. And they have to be at high voltage, otherwise for a given amount of power, the current would be very large, these conductors would have to be very large, right? And a lot of losses otherwise. So that's why we go to 500 kV, 765 kV, and things like that here. So we talked about this power transformer, they step up the voltage, and when they step up the voltage, they step down the current here. So if you look at the energy mix, so this is a slide coming from, I think, Excel website. It shows what it is, and it was actually, I should say, in 2015. Okay, and it shows that we had 54% carbon-free electricity, and what their plan is for 2030, proposed plan, is 63% carbon-free electricity. And these numbers have changed, that I don't know, but this is what I saw, and you can see here that our utility, our state, I should say, our state, thanks to Excel, is pretty heavily nuclear. In 2030, it'll be like 28% nuclear, and wind, which is right now only 14%, or was in 2015, it would be 25%, and solar, which was almost non-existent in 2015, seems to be, is here 8%. Okay, so that's a big change from almost 0 to 8% here. And natural gas, well, it's Natural gas actually has gone up quite a bit because I think coal has shrunk from 38% to 15%. So that slack has been taken up by natural gas to a certain extent. And combined coal and gas in 2015, I would say were, about 46%. And in 2030, according to this plan, they'll be 37%, right? So if you add the numbers here. So in California, they have actually passed, it says introduced, but I think this energy bill has passed, where they have passed that by 2045, 100% of electricity should be carbon-free by renewables, right? So California, a lot of dreamers. It's people in California dreaming on a winter day. There seems to be the mamas and the papas if you're old enough, right? Dreamers. But in Minnesota, they are having problems because of this so famous duck curve. So what happens is the sun shines during the noon hours, right? And the load on the utility system decreases. It dips down. So that's what it's saying. During the noon hours, around 12 p.m. or so, the load that utility has to supply goes down, right? And electricity is one commodity which has to be consumed as it is generated without storage. Without storage, the demand has to meet the supply, right? And so utilities have to cut down on their generation during the noon hour, but then during the evening, when people come home and they turn on their TVs and lights come on and all those things, so around 6 or 7 p.m., load peaks, as you can see here.
They need more wind.
Yeah, that too. They need everything, Mark. So utilities have to ramp up their production. So you see the ramp rate here. So 13,000 megawatt, 13 gigawatt in 3 hours. So that's, quite a challenge, as you can see here. And so the point is, can we follow California's lead? I think we can, but I think with our eyes open, I would say. So one of the things we could do is not throw away, as we retire our coal and natural gas plants, not throw away the generating part of those plants. Okay. So you can see on this slide that on the left, 127 gigawatt of generation has been retired since 2005. Okay. 127 gigawatts. Okay. Giga is what, 1,000 megawatts, right? So why throw away? It'll be a damn dirty shame to throw away the generating part of those retired plants, use them to help the grid. We still need the grid. So we can use those generators and through power electronics, bring them to speed, synchronize it to the grid, and supply some power from the batteries for real power exchange for damping. So that, could be one of the things that we should keep in mind here. So we have wind plants, quite a few in southwestern Minnesota and south of us here, near Rochester. And in Oregon, I think there's a plant which is over 800 megawatts, about 850 megawatts, Shepherd Flats. Okay, then we have this massive solar plants, for example, this one here in Southern California, San Luis Obispo, which is 550 megawatts, and it can supply 55,000 residential homes. So these are massive utility scale power plants. Okay. Then we could have rooftop solar. So this National Renewable Energy Lab, NREL, it's a government lab. They predict that 40% of our electricity we can generate using rooftop solar. Okay, but there are a lot of challenges. Like I showed you in that slide, that the cost of rooftop solar was, four times or 5 times more than utility scale solar. Okay, so it's quite expensive. But to integrate all these renewables, what we need so-called power electronics. Okay, so I was lucky that I got into this field 50 years ago. Okay, so we need power electronics because we have a source on, let's say, left side and the load on the right side, and the source may be photovoltaic, but photovoltaics produce DC, and what you're feeding this power from the photovoltaics is into the utility grid, which is AC. So you can't take DC and feed the power into AC. Won't work, right? So you need this power electronics interface in the middle. So it's really connecting two, different characteristic source and load, and the role of source and load can reverse. Okay, so the power can be bidirectional. So what is load today may become a source, and the source may become a load. So that can happen in a battery, right? Because you're charging the battery and they are discharging the battery, right? So the power has to flow both directions. And this has to do it very efficiently. So, very, very little power loss. So 95 to 98% efficiency is possible, even higher. People can go up to 99%, okay? So very efficient here. So how do we do it in these power electronic converters? We chop up this, whatever is coming in, let's say DC voltage from photovoltaic grid, we chop it up, and then we resynthesize into whatever is required, for example, 60 hertz to feed the load. Or if you have a wind turbine, the frequency that's coming in from the wind turbine generator is variable depending upon the wind speed. It could be 34.56 hertz, but we chop it up and then again feed it into a 60 hertz. So that is all possible thanks to power electronics. And these power electronics converters, as we call them, consist of transistors. So when we think of transistors, we think of these little bit teeny, tiny bit devices like in our cell phone. But they can be very big. They can be size of a personal pan pizza, and if you dropped it on your foot, you could be hurt, okay? So those transistors. So we need them for electric vehicles, for charging and discharging. So what is this Minnesota rectifier here? Well, our university, we had invented this Minnesota rectifier in the early 1990s, okay? And this Minnesota rectifier was used for charging of a fleet of electric vehicles General Electric had produced in the mid-90s. How many of you have heard of EV1s? EV1s, right? So EV1s were produced, they were not sold, they were leased by General Motors. And to charge the fleet of those EV1s was done by using this Minnesota rectifier, but then GM stopped this program. They recalled all these electric vehicles, and they were shedded in Arizona desert, okay? So there's a movie, even, Who Killed the Electric Car? Has anybody seen that movie? Yes, some of you have seen it. Okay. Same people. Okay. So anyway, so I'm looking forward to this autonomous electric vehicles, okay? Electrifying transportation that Jukka will talk about more, but wouldn't it be nice to go with another couple to some restaurant and it's driven by an autonomous vehicle and it's electric, and it might give a different meaning to DWI, driven while intoxicated. Okay, maybe you won't be ticketed for being intoxicated while being driven. Okay, so anyway, we need charging stations. I own this electric vehicle, and I have quite a bit of range anxiety because I drive sometimes to Hudson, to bars and stuff. Okay. But we also need DC fast charging stations, infrastructure that Jukka will talk about, and some of the research we have done applies to this here. So batteries, of course, we should do a lot of research on batteries. That's the future, but also we should not overlook other forms of storage, like flywheel storage. So one of our PhDs recently graduated. He did a flywheel storage project. It's levitated vertically on magnets, and then it's bearingless. So the rotor is kept into the center by electromagnetic forces. So there's a link here. So this young man is now assistant professor at UW-Madison. So just a little bit of propaganda for our group here. We have graduated over 150 master's students over the years. Most of them are employed in the state, 46 PhDs so far, and 11 of those are employed right here in Twin Cities. 2 of them are my faculty colleagues, okay? And so we have a large group, 8 PhDs and 3 postdocs, but we have been very lucky that we have this UMC, I forgot, how can I make the mistake? University of Minnesota Center for Electric Energy, I'm sorry. University of Minnesota Center for Electric Energy, and that was established in 1981. So it is one of the longest lasting centers at the university, and it's supported by 6 regional utilities like Xcel, Minnesota Power, what is that? Rarick Power, and Great River Energy, Sampa in Rochester, and Dairyland Power in La Crosse. Okay, and then we are fortunate to have funding for 1R, NSF, DOE, EPRI, and also we are the first to get this RDF grant that our state has established, right? RDF grant. So the very first cycle, we were fortunate to get that grant here. So I'd like to finish up by showing this last slide that it's really our moral and ethical responsibility, given that poorest of the poor are on the front line. And to like Carl Sagan, some of you probably have seen his show on TV. He says that in one of his clips, Pale Blue Dot, that there is no hint that help will come from elsewhere to save us from ourselves. So I think that's quite a sobering lesson for all of us. And there is no planet B. We call Plan B, but there's no planet B. We can go to Moon and visit Mars, perhaps, but not to settle there, not yet. Okay. So I'll finish up with that, and thank you so much. And brief bios of all 3 of us is here, and I'll, at this stage, Madam Chair, I'll turn it over to Mark here.
I think we're going to take some questions first, because I do have a list of folks who have questions for you.
Okay, sure.
Starting with Representative Long. Okay, Representative Rarick.
Thank you, Madam Chair. And thank you, Dr. Mohan. You're bringing me back to my days at Dunwoody when I went through the electrical program. So with some of the things you brought up, I know you brought up we've got retired generating plants. I would think most of them were probably steam-based. What would be the way that we would be able to utilize those generators going forward with renewables?
Well, whether we use them with renewables or not is not an issue, okay? But when you have a coal-fired power plant, you have the boiler and everything else, right? But in addition, you have a generator. So let's say we get rid of the rest, but just keep the generator, right? So decouple the generator from the turbine. And then we can run that generator as a motor to bring it to synchronous speed and synchronize it with the grid, okay, using power electronics. And that power electronics then could be used to provide some real power exchange from batteries. So that could be an option. But the synchronous machine, the synchronous generator you have, provides the inertia because it's a massive structure, right? So it's rotating, it has inertia. So that is very helpful to synchronize the grid. But you could, we could have renewables too there, right? Because you have the land. And also I would say that you have the infrastructure. You have the transformers there, and it's connected to the utility grid to hold the power when it was a coal-based plant, but now it's not coal-based. So it could apply to gas, it could apply to nuclear. Someday, these nuclear plants we have would retire, right? They'll not go on forever. So we could use that there.
Thank you, Madam Chair. Yeah, that was my question. I was thinking when you said we could use them that we would be still using the turbine to turn the generator. So thank you for that. And then as you talked about California was a great example. So do you basically see that storage is the answer, that without storage, renewables really aren't, we can't go 100% without a good storage system?
For me, storage is really the missing link, right? We need storage. And it is somewhat difficult to imagine how it can be 100% renewable. And without that, I'm sure, I don't know the details, but they are thinking of importing quite a bit of that energy, for example, from Oregon, where they have a lot of wind energy, from Arizona and Nevada, where they could have solar energy, right? So they could be importing that. But without storage, it is somewhat difficult to imagine. But you can have a goal to go to 100%. Maybe you get to 90%. That's good. Better than nothing, right? So, yeah.
Thank you.
Sure.
We're going to have a hearing on storage. We're going to devote one of our sessions to storage. I believe it's going to be the 7th. I'm not positive yet, but I believe that. Representative Swazinski.
Thank you, Madam Chair. Thank you for your presentation. Just kind of, you touched on the fact, looking at kind of the cost-benefit analysis a little bit from industrial solar, wind, and then rooftop. What are your thoughts on this push for, I mean, if you're going to have the conversation of pushing for solar, why on earth would you push for rooftop solar, which is exceptionally more expensive than all other forms? And then I have other questions as well. Thank you.
Right. So what I would say, just my opinion, I've not done any analysis or studies, that, we already have roofs, right? So it's, why not just make use of those roofs? The problem is that, there is no smooth way to install those things. So as I mentioned to you, as we speak, I'm getting a 6.2 kilowatt system at my house, and the panels were mounted, I think, sometime in November, and they have still not been hooked up to the utility, right? So there are different parties involved here, and that makes the cost so much higher. It'll always be higher compared to utility scale solar, right? But I would say that we need everything. And, in California, there's a legislation that if you build a new house, you have to put rooftop solar if you can, okay? But, that's California. We don't have that kind of solar resource here, but I would say we need everything.
Madam Chair, yes, thank you.
Okay.
Want me to follow up?
Yes,
Okay.
go ahead.
Thank you, Madam Chair. And just kind of on a secondary note, just from you talked a little bit, maybe 90% would be a feasible option. Have you done any cost rationale on kind of what the cost per kilowatt would potentially be to get to that point from a transition to where we are today to where that would lead us? And then I have another follow-up.
Yeah. Well, again, that's really not my field to do cost analysis, right? But my feeling is that the cost could conceivably be lower because, if you look at the other costs involved with these fossil fuel-based plants, right, there's a lot of health problems. And we know that our climate is changing, and it's changing because of us. And, last Thursday, Dr. Sanapanini talked about the health effects of, these CO2 and all the pollutions that we are creating. So I think there are a lot of hidden costs that we don't see in fossil fuel-based plants. So, but in spite of that, as you saw the numbers, they are almost 1/2 of coal and gas-produced electricity, but we need to drive those numbers for wind and solar even lower because of the variability here. Otherwise, they'll hit a roadblock.
Thank you. And just one final question. So, in the past, we've used cigarette tax to kind of curb the use of cigarettes, kind of as a tool in the toolbox. Kind of what are your thoughts, to do the same, as a tax on, fossil fuels or gasoline or diesel? Do you think those would be kind of a good tool to kind of help curb the use of those things?
I can, not from an unbiased point of view, but as an advocate of renewables, I would say that it would be very wise to have some kind of carbon tax. Okay, and this year's Nobel Prize went to 2 economists who talk about carbon tax. Okay, so that's, again, something which policymakers have to come up with. So that's what Dr. Gavin Schmidt says, that how governments, societies, individuals, and we us all get together to solve this problem. So we are in it together, I think.
Representative Bierman.
Thank you, Madam Chair, and Dr. Mohan for being here today. I wanted to compliment you on your quotes that started out this presentation. Those really resonated with me, and I'm sure many in the room. And your summary of what needs to be done. It seems pretty obvious that if we can just change those human attitudes in the political climate, we'll be good to go.
I agree. I wholeheartedly agree.
But it will be a process, and we'll keep working on that, and I think everybody in the room has to work on that. I wanted to go back on Representative Swedzinski's question on the solar rooftop, just a clarification on a couple things. I'm wondering, you explained some of what drives that cost, and I understood that part. I'm wondering about those massive solar farms, if the costs for those are less in relation to coal. And also, just if it's a volume thing, you know, as I drive around my neighborhood, I'm seeing more and more rooftop solar. As that increases, will that lower the cost? So that's one question. I can ask the next ones as a follow-up.
Okay, thank you. Yeah, thank you for asking that question. I really think that, the volume, if we have more rooftop solar installed, the cost would come down. So that's one of the reasons I got myself elected to Falcon Heights City Council on Environment. And one of my roles this summer would be to go around and convince people that they should get rooftop solar, because we have this tremendous federal tax credit of 30%, right? That's a lot, 30%, and that will go away in 2019. So this is a time to install rooftop solar, right? So I was talking to this installer. I said, hey, what if 15 or 20 people decide to get rooftop solar at once? Obviously, the cost will come down, right? Because they'll have to send the electricians and others just once, and Excel would come and inspect all those 15 homes at once. So everything would come down. They'll buy material in volume. Costs will go down there. So I think that is certainly in the cards, I think. We just have to work on it.
Okay, thank you, Madam Chair and Dr. Mohan. The other question I had was in relation to the feasibility of microgrids, and if we have any of those in play in Minnesota in particular. And then also, what's the life cycle of our nuclear power plants?
Right. Well, about microgrids, I'm not sure how many we have in the state, but what I hear is microgrids are more for resiliency. Resiliency is different than reliability. Reliability to me means that we need the lights on all the time, right? That's reliability. But resiliency is if there is some natural disaster, some hurricane catastrophe, and our grid goes down, can this microgrid be on its own? So it could have its own generation and distribution system, and then it's also connected to the main grid. So even if the main grid goes down, it can at least take care of the critical load in that area. So I think microgrids are certainly a possibility, whether they're AC or DC, we don't know yet, and they are being thought about for very critical applications like DOD's facilities and things like that, right? Where they cannot afford to lose power. Okay, so they are certainly possible. Now, when it comes to life cycle of lifespan of these nuclear plants, I think it's about 50 years. See, I'm old enough to have seen this Zion nuclear plant that, what is the utility in Chicago? Edison Electric, I think. They had Zion nuclear plant, so it was under construction. So I was studying nuclear engineering at UW-Madison in 1969 or something, turbulent years. I was tear gassed many times, being in the wrong place at the wrong time. I wasn't doing anything as a foreign student. That's dangerous. But so, Zion plant has been shut down. Okay, so it's about 50 years. So that's about the lifespan. Right? So our nuclear plants are getting there.
Okay, and lastly, I just wanted to comment on your comments on the carbon tax. I think we would all be much better off if we called it a carbon fee and dividend. And if we could have a segment on that, might be nice at some point, but I think it's very misunderstood.
I like that. Carbon.
And
So
there
what
are
was
some
carbon
folks-
fee and dividend?
We're not going to get that. Representative Mahoney.
Thank you, Madam Chair. And my question is on the rooftop solar. In your presentation, you have rooftop solar, 184 per hour. Are you including residential and commercial, or is that do you have a separate number for what it costs with commercial rooftop solar?
I think if you go to the slide, I think there's different for commercial and industrial. This is rooftop solar for residences, I think.
Yeah,
Right?
I believe so.
So
Just to clarify,
Right.
the 184 is for residential rooftop?
I'll go to the slide right now. I have the printout here. I won't use the computer here, but we can check. It's on page, it's a fairly detailed slide.
And then if at the same time, maybe you could look and see what commercial rooftop
Okay,
solar would be at that.
let's see if
that
I have the
rate.
number there. So Jukka, do you see the page number here? Oh, yeah, here. Yeah, it's on page, well, page number is hidden by this slide. So it's 14, page 14. So here, well, I think I take that back.
It's residential.
Oh, yeah. Thank you, Mark. Thank you. I'm a little nervous. So rooftop residential is 184.
Yeah,
So
this,
if you go to slide 14, you'll see that that number is for rooftop residential. And then for rooftop and commercial and industrial solar, it's 109. Okay. And then for community scale is 78. And then for utilities, it's 43, as low as 43.
And just one last question. Do you have an idea of why rooftop solar on commercial is so much more expensive than a field out in the middle of nowhere?
Well, again, it's a question of size. So when we talk about utility scale solar, we're talking about 550 megawatt. Okay, that's, size of half a nuclear plant, which may be, 1,000 megawatt. Okay, so it's really the size and the cost of labor, everything else goes along with that, So that's probably the answer. So this utility scale solar is, to install is like $1 a watt here in the United States. It may be cheaper in countries like India, where the labor is cheaper, right? So it's maybe 60 or 70 cents to a watt. Okay, so it's a lot of those factors going.
and all costs are trending down. These costs are updated every year by Lazard, and they've
If
been
you could
trending
put your
down.
name on the record, just,
Yeah, this is Mark Ahlstrom
Okay,
with
thank you.
Energy System Integration Group.
And just one last comment. The nuclear plants of your youth and your tear gassing moments are so much different than what is being designed today. It's a shame that we don't actually look at that as a form of clean energy. But the China syndrome has scared so many people, and there's been so many pictures of these cooling towers shooting steam from their water, and everybody thinks it's some kind of nuclear reaction coming out. It is a viable form, but not one I am going to promote, because I don't need 1 million people at my door. But it has certainly gotten a bad rap, and I believe it's actually being used in some of the underdeveloped countries where they have less regulation and less less inspections, so it's
Yeah,
getting its own set of problems
yeah.
now, and it's going to happen in underdeveloped
Yeah.
countries that don't
Okay,
have
great,
the resources in case of an.
Thank you for asking that question, because a lot of countries where nuclear plants are being designed and probably would be employed, they don't have the resources like we have here. We are very blessed here. We have wind like crazy, right? Our neighborly state of North Dakota and South Dakota, right? So Minnesota is the best place to be in the age of this climate change, I think. And so that's one thing, but also I agree that newer designs are much safer. So Toshiba and Westinghouse, they have designed, for one thing, smaller size reactors, right? Not 1,000 megawatt, but 100 megawatt, because it's not easy to come up with financing for 1,000 megawatts at once. And you don't need 1,000 megawatts at once, right? And they have passive safety systems. So if nothing works, but they're still safe, so they're passive. So the China syndrome you talked about is more psychological today. You know what happened in Fukushima and other places, right? So it's very psychological. So as I understand, a lot of nuclear plants in the U.S. are being shut down because just the cost of operating them is so high, right? Not to mention building them, but to just operating them.
It's just like, I'm not going to drive a 15-year-old car because the cost of repair is much more than the other. So anyhow, thank you.
Yeah, thank you so much.
We have 4 more questions, and then we're going to move to our other testifiers. Representative Long.
Thank you, Madam Chair. So on the Lazard estimates, just to dig into those a little bit, and Mr. Ahlstrom, you touched on this. So the estimates have changed over time. I looked back at the 2009 Lazard estimates, and the wind levelized cost in 2009 was $140 per megawatt hour. Now it's $32 per megawatt hour at the low end. For solar, it was $350 per megawatt hour for utility scale, and now it's $50 per megawatt hour. That's pretty dramatic. What accounts for that dramatic falling of cost, and can we expect that the costs are going to continue to fall?
Yeah, I can answer that, but I think Mark here, I'm just talking about things. Mark actually does things, okay? So it's nice to have, it's okay to have Mark's answer too, right? But I can answer that, these wind turbines are becoming bigger in size, okay? And that, in a per unit basis, it drives down the cost. Okay, so that's one thing. And for solar, there has been a tremendous decrease in cost of solar cells, okay, by many, many factors. 3 or 4 times drop in cost of solar cells. And the system cost, which is on top of these solar cells, is somewhat going down as well. So, these utilities are learning from it, and I didn't say utilities, but these developers like First Solar, and they are driving down this cost. But this cost has to come down much lower, I would say, because of the variable nature of these systems here. If you're really trying to go 100% or perhaps 90% renewable, carbon-free, these costs have to come down.
Representative Rarick.
Thank you, Madam Chair. Not so much a question, but as the microgrid was brought up and the reliability versus resiliency, took me back as my background as an electrician and working with linemen that take care of our grid. Go back to, remember, a little over 19 years ago, the scare that we had when we were going to flip to 2000 and the computers were going to go down and our electrical power was going to go out, and a bunch of people bought generators to make sure they would have power. But what happened with that was when you'd have local power outages and people throw their generators on, and then the linemen go out on the system and they didn't realize they're backfeeding the lines. And so I want everybody to remember as we talk about microgrids and your rooftop solar and all of these separate generating sources, that if the main source goes down and we send linemen out to fix it, we have to make sure we're installing everything correctly so that it's isolating these power sources so that we're not endangering our linemen when they're out trying to fix the main system to keep us all connected to that. So I just wanted to bring that up.
Thank you. Representative Hornstein, and then Representative Bowe, and that then we're going to go to the next testifier.
Thank you very much. Madam Chair, I'm particularly interested in electrification of the transportation infrastructure, and I appreciated your slides on that. What do you see as the biggest barrier to more widespread adoption? The slide you had about with all the Nissan Leafs lined up and the electric charging stations, that's a vision that I hope that we can aspire to. But what do you see are our biggest challenges in getting to that place?
Yeah, I can say a few things. I think Jukka here has much deeper understanding of electric vehicles. I think right now the cost is quite high of electric vehicles, but I think in the long run, if the batteries improve, the cost should come down because electric vehicles are a very simple gadget compared to internal combustion engines, right? So I think for the large part, it's really the batteries and the range anxiety that you have, that my car gives about a little over 100 in cold weather if I turn on the heat, okay, 100-mile range. Okay, so that's one problem, and then the lack of charging stations, right? So all of those things should go hand in hand. More charging stations that I could go to, and fast charging, okay? Because to charge my car would take maybe 20, 30 minutes to at least one half full charge, right? Whereas we go to gas station and we take 1 or 2 or 3 minutes, that we think is a little too long, right? So there are a lot of factors, but I'll let Jukka, address that question. Thanks.
Thank you, Madam Chair.
Okay, Representative Mohan.
Thank you, Madam Chair. Mine will also be quick because it's really not a question, it's more just a statement, and that is I know that many local small utilities are actually concerned about the growing interest in rooftop solar because they're concerned that those rooftop units will not mesh well with their grid and will be problematic for the grid itself, for their local grid. And so they're hesitant to embrace or encourage increasing use of rooftop solar for a solution here. And then certainly not only for the operational concerns on the grid, but also then, as Representative Rarick said, there's also that concern that they'll be feeding into the grid when line workers are out there trying to work on the system. But there's just a lot of concern out there as far as rooftop solar from the individual standpoint.
See, there's a fear of anything new in some sense, right? And so I think today's inverters that feed power from solar into the grid are very well designed. And there are standards which prevent these inverters to feed back in case of line outages. So there's anti-islanding protection built into it, and these inverters can actually help the grid by providing reactive power, as we call it, for voltage support and for frequency regulation to a certain extent. So they could, instead of being a nuisance, they could in fact be aiding this power system. But they should be done with both utilities and the consumers as partners. We are all in it together, I think. That's what I would say.
Yep. I know they're concerned about damage to their grid, and so they currently require greater scrutiny as far as inspections before they allow them to hook into the grid, and certainly that adds to the cost of the system as well.
So that could be at some point streamlined, so that cost hopefully would go away.
Okay. We're going to go on to our next testifier, Ahlstrom. Are we switching? Which one?
Yes, Mark Ahlstrom.
Okay. And if you would, you've got your name on the record now. Thank you.
Thank you, Madam Chair, members of the committee. Mark Ahlstrom. I'm actually speaking here today on behalf of the Energy Systems Integration Group, which is a U.S.-based international group. I somehow ended up as president of the board of that a few years ago, and we're kind of the technical side. The engineers, all of the system operators are members of the Energy Systems Integration Group, but so are the vendors, the people that are developing equipment, the people that are installing equipment, and anybody that's really involved with the technical side. You may know that here in Minnesota, we're part of one of the largest, independent system operators, the Mid-Continent Independent System Operator, which we commonly call MISO.
And that operates a large grid, and we also are a part of an even larger interconnection. Ned pointed out that we're all running at that same 60 hertz frequency. The whole eastern half of the United States runs in synchrony here. We are all part of the eastern interconnection. So we're all in this together. That doesn't mean that Minnesota can't be a leader and do a lot of what we're talking about here on our own and contribute that, but we also have to make sure we have the standards that were discussed and get all the technical issues right as well. And that's what we try to do at ESIG, is to get all people together to share what we've learned and to share studies and really make sure we do it right, we do it safely, we do it reliably, as well as economically. My connection here in Minnesota is strong, though, too, because I really worked for many years in software here in the Twin Cities. When I got out of college, I'm much younger than Ned, so the protests were done, but I moved up here out of college.
No tear gas, huh?
No tear gas for me, but I saw the remains and the design of the buildings down there. I ended up quite unexpectedly in the year 2000 running a company called WindLogics here in town, which came out of our supercomputing and weather modeling background, believe it or not, here in the state, which was quite strong. And I was very involved personally in the integration studies, going way back to 2003, 2004 with Excel, when we were trying to convince Excel we could put in 600 megawatts of wind. How would you possibly do that? We did a great study where we modeled a lot of the weather and the wind and the system and figured that out. I was also one of the PIs on the principal investigators in the 2006 Minnesota wind integration study, and WindLogics developed the state wind maps in 2006 as well. So we've been very involved in what we can do about renewables here in the Midwest and Minnesota in particular. Our real core job, though, of WindLogics was to help people build smarter wind projects, and now we help people build smarter solar and storage projects as well. One of our customers was a company that's now called NextEra Energy, the largest developer, owner, and operator of renewables in the world. It's the company that produces more clean energy than any other company from renewables. They actually purchased WindLogics. We became a wholly owned subsidiary of WindLogics in 2006. We were based for many years in Bandana Square, and we now have a long-term commitment just across the Robert Street Bridge here to what is now going to be called NextEra Analytics, where we've got 100 people and growing of the smartest science and math and software, cloud computing people that are working on how do you optimize the use of renewables and keep everything reliable and economic. So it's a long history here, and we're very proud to be part of the Minnesota community. What we heard about from Ned, though, is the real excitement about the transition in the energy mix and what's going on with electricity. I mean, it's inevitable we're moving toward less coal, more with renewables, more with demand response, more with electrification. I mean, that's why we changed the name of this group that goes back to '89 that used to be called the Utility Wind Interest Group, and it's now the Energy Systems Integration Group, because that system integration and how it all has to fit together is so critical. But the transition, as Ned pointed to, I'm actually probably more upbeat in terms of the costs and how we can make all this work from a group of engineers getting together figured out than even maybe Ned kind of portrayed, because I fully agree that we can come up with a way that is cleaner, more sustainable, but also more economic and more reliable. In fact, I've spent the last 5 years of my life largely at a group called the North American Electric Reliability Corporation, which develops the nationwide standards for reliability for our entire high voltage power system. And it started out where people there were also concerned about, well, how do we do this reliably? Isn't this kind of a disruption? If we retire the coal plants with those big spinning heavy generators, we put on wind and solar and storage that now use these inverters, the power electronics, isn't that a threat to reliability? And we worked that through. We worked for many years on what now is called essential reliability services, which is you need certain core services, these grid services, to keep everything working reliably. But we are increasingly finding out that you can get that from many different places. I mean, Ned was talking about taking the generator piece of a coal plant and keeping that spinning as a motor to provide some of that stiffness to the grid. That's one choice, but there's actually many. And our biggest choice going forward, especially when we get to really high renewables, is to get the engineers and everybody to agree on, okay, we have all this array of choices. Which choice are we going to take? We have to commit to it and do this transition. So it's not a case of can we do it, it's what path do we want to take. So I would stress that today's plants that we're putting in are actually the most state-of-the-art, most accurately responding, and most reliable plants ever. even compared to the plants that we've had. You got to remember, we've had 100 years to figure out how to use coal and gas and hydro plants. It's really only over the last 20 years that we have really gone in deep on renewables, and we've made huge progress. And now they actually are fully embedded as reliable power plants, not just wind farms. In fact, I never call it a wind farm or a solar farm. It's a wind power plant. It's a solar power plant, right? Because it does everything that any other plant can do. Today, we have nationwide standards that every new wind, solar, or storage plant has to have the capabilities of supporting voltage and frequency. In fact, no new plant goes in that doesn't have the capabilities of contributing to reliability in that way. That came from the Federal Energy Regulatory Commission level at the top. At NERC, we have these standards around exactly how these wind and solar and storage plants supposed to behave if there's a disturbance. And now there have been growing pains as we figure this out because, the conventional plants behave fairly slowly, but we're used to that. And we actually had to slow down the way that some of these wind and solar plants respond because they can respond so quickly with their power electronics that it was sometimes too fast. And we had to coordinate it. So it's a coordination issue, especially if we do this transition. But they have the capabilities. We're getting the standards in place. We're touching up those reliability standards. We're working on interconnection agreements so that every new plant that goes in now has to have certain interconnection characteristics for safety, for reliability, and how it's going to respond when something goes wrong. This also applies to the markets. The market rules are changing, like at MISO right now, in terms of exactly how should renewables and storage participate there. How can they provide more than just the energy that we've used them for before? They used to be just, I just want your clean energy. Now I want that clean energy, but I also want you to provide me with these other reliability services, these other ancillary services. So we're in the process right now of adapting market rules so that we can fully get those services from all types of generators. And as I mentioned, some of the really important characteristics of reliability are for the entire Eastern interconnection. And that is coordinated by places like NERC and FERC and these levels as well. But the reality is that we don't have to have all of these services ourselves. Some of them come from Florida when something goes wrong. We're all in this together as part of this larger system. And that's what we do on the reliability and engineering side, is making sure that everything continues to work in that way. But the bottom line is that the new plants we're putting in, whether they're wind, solar, or storage, are state-of-the-art. Yes, we would also like other forms of storage, like pumped hydro and use other resources. We're not, diversity is good. But we are finding ways where actually renewables can do almost all of this on their own if we want them to, and we just have to coordinate that and make sure we do it right. In terms of the 80, 90, 100% debate, I strongly believe that actually with the current equipment that we can buy and install today, that we know how to use, we can get to 80% clean energy quite easily, and I think probably even at a lower cost than we're paying today, with economies of scale as we do more of this. So I think we know how to get to 80% with current technology. We do have to make these choices about how do we get to 100%. I think that, number one, I think we've got 20, 25 years to figure that out. We've got an awful lot of smart engineers that are getting together at meetings like ESIG and others to figure this out. But it's more a case of which choice do we want to take. It's not can we do it, it's do we want to convert even more of it to the inverters and make the inverters support the grid? Do we want to keep some of those big, heavy spending things around and continue to use frequency in that way? And that has to be engineered, that has to be a conscious decision. But it's not a can we do it, it's which way do we want to take to do that, right? And finally, I just pointed out that, we are part of this system. MISO, the system operator here, is a state-of-the-art, very progressive group that's part of this, but so are the standards and what happens at our utility commission, our state standards, what we do with our distribution companies and how they interact with the transmission companies and so forth. But we have an awful lot of good people working on this, and it's never been a more exciting time. So I'm extremely optimistic. Not only can we do it, we have choices, and it's going to be a lot of fun to figure out which path we want to take to get there. Thank you.
I think we're going to hear from my final testifier, and then we will do questions. I would like to go back and talk about some of the things you said, but thank you. And if you would introduce yourself for the record.
I will.
Madam Chair, representatives, my name is Jukka Kukkonen and my company is PlugInConnect. I work as an EV market consultant here in Minnesota, and I've worked with electric cars for the last 10 years and been involved with pretty much everything that has to do with EVs in our market. I work with utility companies, auto dealers, advocacy organizations, manufacturers, universities, EV owners, and a number of other stakeholders. So my main job is to stay on top of what's happening in the market and provide really good real-life information for all stakeholders about EVs and the market. I'm an automotive engineer by training, so I used to work at the Ford Motor Company in Europe. So because of my background, I always start by looking at everything from the technical perspective and then go to a market from there. So we've heard already a lot about how does grid work and how is that all working. So I'm going to be providing hopefully a little bit more information on how do EVs play a role in this grid and how can they help with the whole system. So here's the first we've talked about the macro level, I'm going to micro level right now. So this is actually a residential household, and it's my house in Highland Park, St. Paul. And this graph shows 24 hours of my household electricity consumption, January 16th of last year. So it's a year ago, 24 hours. So on the x-axis, you can see the hours there, 24 from 12 a.m. to 12 a.m. And then on the y-axis, you can see the power level from 1 kilowatt up to 10 kilowatts. So higher the graph is, the higher the power consumption right now is. So if you look at that, that's my basic household consumption right now there. So I'm consuming less than 1 kilowatt in general over a 24-hour period. So my house is decently energy efficient and LED lighting, energy efficient appliances. So that's good. So I'm not great customer for Xcel Energy at this point. I mean, I'm consuming some, but I could consume more. But this is what we are seeing. Then when you add into this one that I have solar on my rooftop there. So then that green portion that you can see now there is my solar production in January 16. And January 16 is not the best time of the year to produce solar, but still I'm producing more than I'm consuming for that day. So at this point, I'm starting to be a horrible customer for Xcel Energy. And when I speak with the smaller rural utility companies, they say at this point, Jukka, let's make one deal. You don't move to our service territory because we don't want more of your kind of customers here. You just keep on being with Xcel there. And that's fair. I'm really not providing too much value for them with this kind of setup. So what are the utilities should be doing in this case? Because they will see more and more these kind of customers. Energy efficiency is improving, better appliances, better lighting, everything. Many of them are considering the solar rooftop and so forth. So what's the magic bullet here? Well, if they can convince their customers that you should consider driving an electric car, this whole picture changes quite a bit. Now we have 2 cars of electric cars in our family, and that's our charging for those electric cars. So if you look at those graphs, the bigger graph there is actually my wife's charging her Nissan Leaf. She drives 35 miles a day, and that's the energy consumption that hits there. I didn't drive too much on that day, so my consumption was lower. If I would have driven the same 35 miles, it would have been the same. So I actually start to be a pretty decent customer for Xcel with these graphs. And the rural utility companies are saying to me now, okay, now you can move to our territory. We're happy to have you as a customer. Because in addition to those being increasing the load will happen during the nighttime when there's less load on the grid. So electric vehicles provide a great opportunity for utility companies and the grid. EVs can easily be charged when the grid is underutilized and the cost of electricity is low. So EV charging will increase utility company revenues without the need to upgrade distribution infrastructure. This will be a good example of beneficial electrification that will put a downward pressure on electricity prices, and this way benefiting all electric utility customers. EV charging can also help the renewable energy integration that we've talked about already here. by consuming the excess production. They are very good flexible load. In my household, for example, we are just setting my charging station so that it can follow the solar production and charge the car while there's an excess solar production in my household. We can do the same in a bigger scale with grid level controls on a larger number of cars. So this is also doable. So let's look at the market then, what has happened in the market in the recent years. So EV market has been growing pretty well in the last years. In 2018, plug-in vehicle market increased by 80%. Our challenge is that the vast majority of this market growth in last year was produced by one manufacturer, Tesla. So if you look at that graph there, the top one is the pink one there, that's Tesla Model 3. Just one model practically changing the market last year. So Tesla really showed us that there is a demand for electric cars. There's no question about that. No one can kind of say that anymore. Since September, Tesla Model 3 was every month among the 5 most sold passenger cars in the US. In some months, they sold more Tesla Model 3s than Toyota dealers sold Corollas. So that tells something about it. So why is Tesla dominating this market segment last year? It is because all the other 3 models from other manufacturers have so short driving range that people are not buying those because of range anxiety? Well, I don't think so. If you look at the list that you have there you should have a separate list of all the plug-in vehicles available in Midwest and in Minnesota here. So if you look at there, in the middle of that, there's a column there that says total range. And you look at those ranges, they're not that different from traditional internal combustion engines. The shortest range there is 151 miles. That's a Nissan Leaf range for that one. The same model was when we bought our first one in 2012, it got 73 miles. So it has already improved double from that. And in just a couple of months from now, Nissan will offer an option with a bigger battery, which will be over 200 miles. So since 2012, the range of that car has tripled. So average driver drives 37 miles in the US. So depending on what you use, you just choose the right car for those things. So technology is moving forward. So if the range is not an issue, how about the public charging? That has been often said that, okay, that's a problem. If we don't have enough public charging, why would people drive electric cars? First of all, many organizations have done a great work in this front. So according to DOE, we have 327 public charging locations with 808 stations already in Minnesota. That's a pretty good number. This is not to say that we don't need more. Definitely there's more, especially for the corridor charging. But it's not really a reason why manufacturers couldn't sell electric cars in Minnesota anymore. Especially when you think about it that, as I showed in my graph there, people charge at home. 85% of the charging happens at home. My wife has driven electric for the last 6 years, and she hasn't used a public charging a single time during that time. She just comes home, plugs it in, lets it charge overnight, and in the morning it's full. That's the easiest and most affordable way to power your driving. So it's not that hard. So if driving distance is not the limitation and the charging is not necessarily the limitation, there's of course a lot of education that needs to happen. That's definitely clear. But traditional manufacturers have said that in the past that there's not enough customer demand, but Tesla clearly has proved with the Tesla Model 3 that that's not true anymore. As part of my work with utility companies, I visited over 90 dealers last year, and I also trained over 200 auto salespeople on how to sell plug-in cars. Through these discussions, it has become very clear to me that our biggest challenge at the moment here in Minnesota is that auto manufacturers are not providing enough units for our dealers to sell. First of all, as I said, we have 45 plug-in vehicles available in US, only 26 of those are available in Minnesota. And even those 26 that you see on the list, auto dealers might get 1 or 2 units per month or something like that. And that's not how to do other business in Minnesota. We know that. Dealers will sell what is on their lot. If they don't have it on their lot, they are not selling it. If they don't have it on their lot, they are not marketing it. And if they are not marketing it, people are not hearing about it, they are not coming there to ask for it because they haven't even known that it's available. So that is the challenge that we have right now, is that we just don't get the cars right now for us. And this is kind of a self-fulfilling prophecy, and it doesn't really help us Minnesotans. So generally, to sum it up, powering our transportation with electricity will increase the utility company revenues. And based on the recent study by MJ Bradley and Associates, it will also benefit all utility customers in Minnesota, not just those who drive electric. EV owners will also have to spend less money for their driving because it's cheaper to drive electric, so they can spend that money in other uses. Shifting to electric transportation also means that we need to import and burn less oil, which will leave more money, of course, in Minnesota economy. It will improve our air quality and reduce greenhouse gas emissions. And as mentioned before, EV charging provides an excellent flexible load that can be used to level the grid loads whenever needed. So for all of these reasons, EVs are a win for the grid, they are a win for the utility companies, they are a win for the consumers, and they are a win for all Minnesotans. And this is just starting. We're just getting started with this, as we are with renewables in many ways. The same way as cell phones have changed how we communicate, the EVs will change how much energy we have to spend for our transportation, and it also enables us to move to renewable energy production to power our transportation. Thank you.
We have about 2 minutes and 3 questions on the list. So if we could be quick so everybody gets a chance. Representative Swedzinski.
Thank you, Madam Chair. Thank you for your presentation. Just kind of going back to your graph that you kind of produced, just kind of, you got that center portion there. I don't have a page number on it, but that center portion of where you're producing the most from your rooftop solar, I'm guessing that you're kind of pushing that back into the grid, kind of, and just kind of, so you got your 2 humps on the outside and you got your hump in the middle. And if you don't have this handy, you can email it to me or whatever, but just from so like those humps on the outside, what is the cost that you're paying for that electricity, so off-peak, and then what you're being paid for that center, for the electricity you punch back in, just the difference in cost, if you happen to have that. And then I have just one other question when it came to production. It looks like, from most of the grids that we are not increasing our need for electricity, and because we're not increasing our need, just because we're expanding production of electricity for electricity we're maybe not consuming, so we're having duplicity in our market, what that is going to be the potential and, by government regulation, that sort of thing. So go ahead.
Okay, Madam Chair, Representative. In my case, I could go either time of use rate structure here, or I could stay in a flat rate. If I'm in a flat rate, I'll be getting paid the same or net metered, so that at the end of the month, it'll look how much I've produced and how much I've consumed, and I'll pay the same money for that. Okay. So I'm net payer right now because of my consumption, even if I have solar. In my case, if I would be at the time of use rate structure, when the time in a daytime I would be paying more, and in nighttime I would be paying less for general consumption. But if I'm at Excel, at least I don't have a net metering for that. So that means that I will not be paid full price, the higher price during the daytime, but I'll just be paid avoided cost for that.
Representative Long.
Thank you, Madam Chair. Mr. Kukkonen, your story about availability of electric vehicles rings true for me. My wife and I needed a new car and bought a Chevy Bolt. We had to drive a considerable distance to find one of 2 Bolts that were on a lot. And they marveled at how fast they were moving off of their lots and how difficult it was for them to keep on, but they only had two options. I'm curious, are we seeing that manufacturers are selling more electric vehicles or different electric vehicle models to other states than Minnesota?
Yes, Representative and Madam Chair. Yes, that's definitely true. Right now they are putting bringing the most models into the states where they have most active legislative or other incentives in place or mandates. So, for example, our market right now, on US in general last year was 2.1% of US car sales were plug-in vehicles last year. In Minnesota, we're a little over 1% on that one. In California, they are 10% already. So that's a huge difference there. Of course, there's differences between states otherwise, but it has a lot to do with availability of the vehicles too, and what kind of mandates or incentives are in place.
Final question, Representative Rarick.
Thank you, Madam Chair. On your chart about the electric vehicles, can you help me understand your charging speed column a little better? It's listed as miles per hour. I'm just kind of wondering, excuse me, if you can help me understand what the time actually is to charge.
Representative, that comes from calculation of how fast the charging speed is there. So if you're, for example, charging a 3.3 kilowatts power, then you look at how much the energy that car consumes normally, and from that calculation you get how many miles you can get by charging that car for 1 hour with that power level.
So then according to your chart, you're saying if you charge for like the Audi on top, at level 1 it's 3. So if you charge for an hour, you'd go 3 miles? Or that's what I'm trying to understand.
Representative, that's correct. So you would get 3 miles for that. That is level 1 charging is if we would plug it into normal 120 outlet. We're limited by how much power we can pull that 120 outlet, and that's why the charging speeds are pretty low in that one. Level 1 charging works really well for people if they drive less than 30 miles a day, because normally cars stay overnight over 10 hours, so you can charge the 30 miles and that'll be fine. And for example, the Audi A3 e-tron that you used as an example has a shorter electric range. It has only 17 miles, so it can easily charge that in for 5 hours probably full. Thank you.
Thank you all so much for coming. We appreciate your testimony. It's just great to have this basis before we go forward. With that, meeting's adjourned.
Thank you very much, Madam Chair.
Thank you.